2,949.6 years.
A little under 3 kilometers. That sounds about right. Okay, so if our sun, current mass, shrank down into, I guess the distance from Peters Creek to Haynes Mall Boulevard, I think that's roughly twice that, since that's a radius, it would be a black hole, because there could be nothing that could go fast enough in order to escape it. Now, will our sun become a black hole at some point? Probably not. In stars, according to current theory, there's two things going on. You've got a whole bunch of atoms in there. Well, it's got mass. So it is pulling in on itself with its gravitational pull because of all the mass that's there. At the same time, we are creating energy, and that energy has to get out. So we have, if you take two hydrogens and smash them together, you create a helium plus energy. So I have two hydrogens here, they float around, they create two heliums. The helium that is created is less massive than the two hydrogens. So there is a loss in mass, that mass goes into energy. Famous formula, E equals mc squared. The radiation, that energy comes out in the form of radiation, and that is creating this outward pressure. So we have this gravitational force trying to pull it in, we have this radiation pressure trying to pull it out. Eventually, we're going to run out of hydrogens, in which case the smallest thing that's going to crash into each other are two heliums. If two heliums are going fast enough, they'll smash into each other, and they'll create a, whatever the 4 is on here, beryllium. Plus there's going to be some energy. Now, the biggest bang for the buck is the hydrogens. Take two hydrogens, smash them together, you're going to have the biggest loss of mass, therefore the most amount of energy. And I'm bleeding. Okay? We're going to take a pause here. I'm going to go deal with this. I'll be back in a couple minutes. If someone would be kind enough to pause. Or I will pause this. Okay, so we have these two different pressures. We have this gravitational pull pulling it in, radiation pressure coming out. So we're losing mass as we go. Oh, one other thing I was going to mention. Oh, I guess I didn't clean that up well enough. To my knowledge, I have no hideous blood diseases. So on the periodic table, we have iron, which is right there. Yeah, there we go. So we have iron. So anything that's before iron, number-wise, is going to, you'll gain energy by smashing them together. Anything after iron, you're going to gain energy by splitting it apart. So the atomic bomb, you take uranium down there, which is the last natural one. That, we use uranium in the atomic bomb, we split it apart, it's called fission. When it breaks apart, it releases energy. The hydrogen bomb works on the other end, where you take two hydrogens, or a whole bunch of them, smash them together, and you get energy out that way. There's much more energy released here than there is down there. The trouble is, getting enough of those hydrogen atoms going fast enough so that they smash into each other is very difficult to do. Hydrogen bombs do not have any natural radiation associated with them, unlike the atomic bomb. However, in order to get enough energy to smash the hydrogens together, we actually have a small little atomic bomb inside the hydrogen bomb, and we use the atomic bomb to trigger the hydrogen fusion. But they're also trying to see if they can work this out to create really cheap energy. And I know they've made a lot of progress over the past couple decades. Not quite there yet, but they're trying to produce enough energy so that it can, in essence, set up a controlled chain reaction so that we can have small little hydrogen bombs without the radiation to supply our electricity. Okay, questions here before we actually get into our sun, again.
Are they doing that because that's the cleanest way to create energy?
If we can get it to work.
Cold fusion, they've been talking about forever.
Yeah. The whole cold fusion thing, that was I guess, I don't know, if, guessing only maybe 3 of us who remember the cold fusion bit. So, I guess 2 of us.
Two. Sounds right.
The big thing is, if you could get 2 hydrogens to smash together and create energy, basically at room temperature, otherwise it's cold fusion, that would be incredible. It takes only a little bit of energy to get that thing going. And in the early 90s, I was out of college, but I was still teaching high school at the time. There were these 2 chemists who said, from Utah, I think it was, who said that they figured out cold fusion. It was pointed out it was also right before a funding cycle, and they were trying to get more money. So there were a lot of experiments done all over the world to see what it was. It turns out that there were people at small universities throughout the world who were able to reproduce it. People at major universities were not. And then eventually figured out it was not cold fusion. It was, I forget what the actual explanation was, but there was something else going on. But cold fusion would be close to limitless energy for the lifespan of humans. All right, so the sun is losing mass as these hydrogens collide, and then heliums and whatever, as they collide, combine, radiation comes off, the sun is losing mass. As it loses mass, there's less gravitational pull, and so the sun will start to expand. If the other way that it could happen is that the mass, there's a lot of mass, but you're not producing much radiation, and so basically it's going to collapse, the radiation pressure gets smaller and it's going to collapse in on itself. Our sun is expected to run out of mass faster than it runs out of the radiation, so our sun should keep expanding. According to current theory, our sun should eventually be here. Now, some people will say that the Earth, eventually the sun is going to swallow up the Earth. Probably not going to happen, because the Earth, as the sun loses mass, the Earth is going to start moving farther away. So the orbit of the Earth will be out there. The sun will eventually be here, but the Earth will be gone by then, as it moved. If there's enough mass so that when the radiation pressure dies out, it comes collapsing in on itself, a couple things could happen. One, it collapses in on itself, it creates so much heat in that as it collapses in on itself that it then explodes, and we have a nova or supernova. It collapses in on itself, and there's so much mass that it might try to explode, but it still can't throw everything off because there's too much mass, and you have, in essence, the black hole.
Which, when it starts sucking things in, the black hole?
Pardon?
So what happens with the black hole? It starts to suck things
Okay.
into it?
So, if our sun became a black hole right now, in about 8 minutes, everything would go dark. But the Earth would still be going around the sun, fat, dumb, and happy. The gravitational pull would still be the same. The deal is that if you've got a black hole now, anything that gets within a certain radius, within the radius, this radius right here, would not be able to escape. And so, by that token, as things come into it, it will gain more mass, this number gets bigger, and the black hole grows. At the same time, it also loses energy as it does this. So the question is it going to gain mass / energy faster than it's losing energy? Don't know. And there's probably several different theories out there. What amazes me is that we know anything. We are in this tiny little spot in the universe, looking out at other stars, trying to figure out what's going on, and we come up with some amazing conclusions. But it's all a matter of, hey, we think this is gonna happen, well, it seems to fit the physics we know already, is to fit what we observe. Sometimes yes, sometimes no. So, anyway. Questions? Let's see, where I want to start this. So now let's take a look at an orbit. I've got some central body, it could be the Earth, the Sun, something that other things are orbiting around. Still called X. So we're not dealing with things going away from it, we're just dealing with a planet or some central body and an object in circular orbit. What is force diagram? What are the forces acting on this object orbiting?
Forced to do
Yeah. So I got a force due to gravity there, got a force due to gravity here. I'm assuming that the central body is so massive, we're not worried about its wobble. I know F equals ma. So that F equals ma. That force due to gravity is equal to the mass of that object times the acceleration. If it's going in a circle, what kind of acceleration is that? Angular acceleration is if it's sped up as it went around. What is the acceleration based upon changing direction? Chapter 8.
Centripetal?
Say it again.
Centripetal?
That's the one. So I know the gravitational formula, that's the force formula, gravitational constant times the mass of that planet times the mass of that object orbiting over this orbital distance squared, so that's just that r squared, is equal to mass of the object times centripetal acceleration. There's a formula for that. What is the formula for centripetal acceleration? It's not 2 pi in there.
B squared over R.
Yeah, that's the one I was going for. Let's hop back for a second.
Just make sure you didn't already do this part.
All right. So v squared over r. Let's get rid of some stuff. What's common to both sides?
Mass of the object.
Say,
Mass of the object.
all right, mass of the object. That goes away. Anything else common?
So R on both sides.
Yeah, I got r squared there, r here. If I multiply both sides, I can get rid of 1 r from each side. So I'm now left with big G times the mass of that planet over r is equal to the speed of the object squared. What's the formula for speed?
Distance over time.
Yeah, speed is distance over time. So if I got something going in a circular orbit, what is the distance it travels in one orbit?
The circumference.
Somebody say it loudly.
The circumference.
Yes, it's a circumference. What's the formula for the circumference of a circle?
By R squared.
The other one.
Mass area. 2.
You've now combined the two. What was it you had?
2 pi r.
That's the one.
Yeah.
So 2 pi times r divided by the time it takes to go around once. What is that time it takes to go around once? I'm trying to remember if I talked about that before. If that were the sun, Earth, yeah. Well, actually, sorry, if that's the sun, Earth, that would be a year. But the name we have for it, if you have something that's doing repetitive motion, I think we can agree, the sun, Earth going around the sun is repetitive, or moon going around the Earth. The time it takes to do it once is called the period. And the symbol for the period is a capital T, which is why I don't use capital T for tension. The period. That will show up again in chapter 19. Time to complete one cycle of repetitive motion. I know it's a little bit of an alphabet soup here, but getting someplace with it. So I'm basically going to take this right here, and I'm going to put it in here where I've got v squared. So I've got this gravitational constant times the mass of that central body over the orbital radius is equal to distance over time squared. I'm going to square this stuff, so I get g mass of the planet over r mass of the central object, over 4 pi squared r squared t squared. Just squaring everything inside here. I'm almost done. I'm going to take all the stuff that we would know, like the mass of the central object, the constant, 4 pi squared. I'm going to stick all that stuff over on the left-hand side, everything else over on the right-hand side. And so I've got g times mass of x over 4 pi squared is equal to r cubed over t squared. I assume I have not derived that before. All right. Why did I do this? Over on the left-hand side, big G 4 pi squared are the same number regardless of what the central object is. The only difference between this, I was talking about things orbiting the sun or things orbiting the Earth, is the mass here. The mass would change. But for anything orbiting the same central object, this ratio of the orbital radius cubed over the period squared is constant. Or more realistically, pretty darn constant. That is one of Kepler's laws of planetary motion. He figured out that, and the fact that he was able to do this without knowing any of this stuff, he figured out based upon observations that he looked at the planets that we knew at the time, how long it took the planets to go around the sun and how far away the planets were, and he figured out this ratio works. 40 years of his life coming up with his 3 laws of planetary motion. The cruelty joke, or skit, that I always imagine is that he and Newton are in a bar talking about what they did. Kepler goes, I've been working on this problem for 40 years, I've almost got it. I've got these 3 laws of planetary motion, and Newton said, oh, you have an afternoon? I'll show you how to do it. We can do with Newton's laws now, we can derive what Kepler took 40 years to do, we can now do it in an hour. They did not overlap, so that historically would not have happened. And one of the reasons Newton's laws were accepted so quickly is the fact that you could derive Kepler's laws from them. The other cruelty skit, I imagine, is the person, the Egyptian who figured out, or Greek who figured out the radius of the Earth by setting a stick up and looking at the shadow. That he sets it up and it's an overcast day that day, or he sets it up and it falls over at the last moment. And then he has to wait another year. If you bring elliptical motion into account, this r stops being the radius of the orbit, but the average radius. If you were desperate to see the actual derivation of this, I do have a set of about 9 videos, calculus based, where I go through it. Starting, in essence, Newton's laws of math. On that note, I do need to talk to, Ms. Katora's not here, Priscilla and Riley, and I think that's it. And I have stuff to hand back, which I can hand to you